So welcome to this video in our continuing series where we're talking about number bases. Alright, in the previous video we would have ended basically by giving a few random examples of numbers where we would have shown that all the numbers are basically combinations of powers of 10. Sum of powers of 10. Alright, a sum of powers is a nice phrase to remember. So what I'm going to do now is demonstrate using another random example, just to go even further to demonstrate that powers of 10 essentially are what we use when we count in base 10. And with that now we set the stage for the switch from base 10 to other bases. Excuse. So let us say we have the number, random number, let us say we have the number 485.962. Alright, 485.962. That is something that we could all recognize. We know that this is 5 units, we know that this is 8 tens, and we know that this is 4 hundredths. We know that this is 9 tenths, as in 9 over 10. We know that this is 6 hundredths, as in 6 over 100. And we know that this is 2 thousandths, which is 2 over 1,000. So, what's happening here now? We have, let us switch the color of the ink here, right? We box into our corner here. And we see now that this is, let me see how much space we will need. We will need, let us say, units, now, become like all here, so units, tens, hundreds, right? And then this will now be tenths, big difference, tenths, this would be hundreds, and this would be thousands, right? Thousandths, big difference, right? Alright, so this is essentially what we have. So this number here is 5 units. This number here is 8 tenths and 4 hundredths. That we understand instinctively. Tenths now, we're going into the decimal side of things now. This is 9 tenths. This is 6 hundredths. And this is 2 thousandths. Yeah? Alright. So, let me make another line here. Alright. 4 hundredths is the same thing as 4 multiplied by 100. 8 tenths is the same thing as 8 multiplied by 10. 5 units is the same thing as 5 multiplied by 1. 5 multiplied by 1. 9 tenths is the same thing as 9 multiplied by 0.1. 6 hundredths is the same thing as 6 multiplied by 0.01. And 2 thousandths is the same thing as 2 multiplied by 0.001. Now, 100, remember we counted in base 10, right? So how are we going to demonstrate that? We know that, yeah, don't mind it, the whole table looking a little twisted and thing, right? We know that 100 is 10 to the power of 2. So this is the same thing as 4 by 10 to the power of 2. This is the same thing as 8 by 10 to the power of 1. 1 we know is 10 to the power of 0. So this is 5 by 10 to the power of 0. This is 9 by 10 to the power of minus 1. This is 6 by 10 to the power of minus 2. And this is 2 by 10 to the power of minus 3. Alright, now just as a matter of interest, alright, this 9 here, here, and here. Alright, let me see where I could put that. I don't think I need any more space here, so I could chuck that in the corner here. 9 by 0.1 is the same thing as 9 by 1 over 10. 6 by 0.01 is the same thing as 6 by 1 over 100. And 2 by 0.001 is the same thing as 2 by 1 over 1,000. Alright? 2 thousandths, 6 hundredths, 9 tenths. I don't want to get too far into this because that will take us into indices, which I don't want to go too far into because I will kind of get distracted there from the central topic of what we're trying to talk about. Alright, so we have taken one number, 485.962, and broken it down into hundreds, tens, units, tenths, hundreds, thousands, following the format that we are accustomed with. Alright, from ever since primary school, that is where we normally learn these things. Units, tens, hundreds, thousands, tens of thousands, hundreds of thousands, millions. And then we go in the opposite direction. Tens, hundreds, thousands, going down the road. And we break it up, 400s going down the road. And then we break up the English now into maths, 4 by 100. And we go even further with the maths, into powers of 10, 4 by 10 to the power of 2. So this line in red here is the first place where we could actually start seeing, literally, that we're counting in base 10. Because every single digit of this number has just been expressed as a power of 10. Alright? So that when we talk about, going back to my definition now, the base of a numeral system being that number whose successive negative integer 0 and positive integer powers, look at here, negative integer minus 3, minus 2, minus 1, 0. You'll only ever have one 0 power, and then you have the positive integer powers here, 1, 2, going up 0. So this is what we mean when we talk about negative integer 0 and positive integer powers. Alright, I basically are going the extra distance to explain the definition, because a lot of times in maths you have these definitions that if you just read it at face value, it can be extremely complicated. But then if somebody were to take the time and explain it, you'll find that it's not so hard, it's not so difficult, it just needs a little explanation, which is what we're trying to do here. So negative integer, boom, 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 0, boom, positive integer, alright, are summed to give numbers with specific and unique values. So let me deal with the summing one time. So this is the same thing as, going back to the top here now, alright, this is the same thing as 400 plus 80 plus 5 plus 0.9 plus 0.06 plus 0.002. That is what it is. So any number we could think of can be broken down into the sum of powers of 10 like this. Now this is the same thing as 4 by 10 to the power of 2 plus 8 by 10 to the power of 1 plus 5 by 10 to the power of 0 plus 9 by 10 to the power of minus 1 plus 6 by 10 to the power of minus 2 plus 2 by 10 to the power of minus 3. Alright? So we have taken this number and expressed it as the sum of powers of 10. But there's one more thing missing, which is what I cover in the second paragraph of my definition, where I say that each power of the base is multiplied by a constant coefficient to give a product. What is this constant coefficient? Without going too far into the definition of what a coefficient is, all we could say, looking at this, is that here the constant coefficient is 4 here, the coefficient is 8 here, the coefficient is 5 here, the coefficient is 9, the coefficient is 6, and the coefficient of 2. So in other words, at every stage, we multiply the power of 10 by a constant coefficient. In this case, the constant coefficient is 4. In this case, the constant coefficient is 8. In this case, the constant coefficient is 5. In this case, the constant coefficient is 9. In this case, the constant coefficient is 6. And in this case, the constant coefficient is 2. Good? And then we can sum this and end back up with this. So I'm going to rub this table off here now. You looking at it on the video will always have the advantage of simply being able to rewind if you need to see the table again. So we erase just to finish this working here. Alright. So we break that down and then we build it back up again. Alright. Alright, so I went back to front. So this is what this is. So if I have to write this out, it will be 400.000. This is 400 and every 400s and everything is 0. Everything else is 0. 8 0 0 0 5.000 and then you have 0.900 0.060 and 0.002. Alright? This is the breakdown of this. And then you add it up. You get the 2 here, the 6 here, the 9 here, the point here, the 5 here, the 8 here, and the 4 here. And that, ladies and gentlemen, boys and girls, is what base 10 essentially is in terms of the regular practical use to which we put it in our daily lives. So any number that we could think of, generally speaking, for all intents and purposes, is base 10. And once we're talking about base 10, it means that the number itself can be written as the sum of powers of 10. That sounds so nice. Don't worry, I'll make a nice little note on it too. Any number that we could think of can be expressed as the sum of powers of 10. That is essentially what it is. The sum of powers of 10. Of course, each of those powers will be multiplied by the relevant coefficient to give a particular value, which we then sum, we add it to get the final specific and unique value of the number under consideration. But why did I take all this time to go through all of this? Why didn't I just jump and start adding in base 5 and trying to transform base 10 into base 5 and all that? The reason being that my method, my modus, is to start with the familiar. Start with what we know. And usually what happens is that we can take something, in some cases everything, from the familiar and transpose it into an unfamiliar situation. We make the relevant adjustments and we move on. So for example, if we know that this is what counting in base 10 essentially is, and I come to you and I say, alright, let me start thinking about base 5. You know immediately that if we count in base 5, the only difference will be that instead of powers of 10, we would now be dealing with powers of 5. That is it. And if I come to you and say, we're going to count in base 3, at that point, the only difference is that instead of powers of 10, we're talking about powers of 3. Alright? And if I come to you and say we're counting in base 2, or base 20, or base 8, or base 16, The only difference is that instead of powers of 10, we're talking about powers of 2 or 3 or 8 or 16 or 5 or 20, etc., etc., etc. So, having laid the foundation by taking the extra time to talk about base 10, we now could start tiptoeing into bases other than 10. Alright? And that is what we will do in the next video in this series. So stay tuned, stay on board, spread the word, and look out for the next video coming your way.